Okay then guys, just a little intro for this section. I'll just run you through a few standard functions that we see appearing time and time again. The e to the x function, well that looks like, if I just draw it in here, here's e to the x. When it tends to naught here for large x negative, e to the naught is 1, so that's the e to the x curve then. If ever we get an e to the x or e to the 2x or e to the 3x, e to the minus x, well that's the same sort of curve but just reflected through the y-axis. So it's the other way around. This is still 1 of course, because e to the naught is 1. So that's what we get there. So that's the characteristic shape of e to the x and e to the minus x, and any multiple of really. And then let's have a look at log. Well, log is the inverse of e to the x. So what you do is you draw the same curve, the exponential curve, but instead you interchange the y and the x axes, so you flip it round. So this is the log function then. Log of 1 is 0, and you'll notice that it's not defined for any negative values. So when you ever want to sketch graphs, plots with log x in a combination of, then you don't need to consider the negative axis. So that's the log function there, and that's the typical shape of the log function. Now x e to the x, when you're looking at products, what you generally do is you draw in the two curves and then you have a little look. So if I was drawing this one, for example, I'd draw the e to the x curve just to help me visualize what I've got here. It's defined on all of x, isn't it, e to the x? This value is 1 here. Not that that's of much interest though, really. And then you can draw the curve y equals x, so let's do that as well. There's the line y equals x through the axes, straight line, gradient 1. You can apportion what scale you wish, so that you can draw it so it's easy on the eye. So now if you want to do the product of these, when x gets large, it's going to be, this goes to large and large, so the product will be even larger still, so it's going to shoot up, isn't it, to infinity up here. So it's going to come down from up here. Now what happens when x is 0, it hits 0, so it goes through 0. And now when x gets large negative, so it shoots up here, and when x gets large negative, we've got a positive times a negative. So it's going to be in this quadrant here. When on the other side, when it was positive, we had two positives, so we know it's going to be in this quadrant for starters, don't we? And by the same token, positive times a negative is negative. Now which term dominates? Well, this is just x, and this is e to the x. This one goes very much smaller than this one goes large. This term dominates in a sense, doesn't it? So the product will get very, very small, but negative. So it's going to come along here. Now when x is 0, it goes through 0, and then it shoots up. So it looks like it's going to come around and then shoot up, isn't it? So we're going to guess that, and it's obviously not going to go down as low as that. But this is the characteristic shape of the curve, isn't it? And then tend towards 0. So let's work out where the minimum is then, and we can do that by finding the turning point here. So let's do that then. So if this equals y, let's just get y dashed. It's a product, so we use the product rule. U dv dx, e to the x differentiates to e to the x plus v, e to the x, times du, x differentiates to 1, let it equal 0. Take the e to the x outside a bracket, because it's common, and that tells us then that the turning point happens when x is minus 1. From the sketch, the way we've done the sketch, we know it's a minimum, so we can leave it as is there with x minus 1. So this value is minus 1, and then when we put minus 1 in here, we'll get the y value. So let's just mark that down here. Minus e to the minus 1, which is minus 1 over e. So it's like minus a third or something, just above that, and just below that, minus a third. So it's doesn't go down very far, doesn't it? But for the purposes of the sketch, this gives the essence, doesn't it, of the shape of the curve that we want. So that's the sort of process that you'd go through when you're looking at combinations of functions that you know how to draw. Because we knew how to draw y equals x, we knew how to draw e to the x, and then we looked at the combinations of and how it behaved. And the turning point was helpful. So in a lot of these examples in this section, finding the turning point is quite helpful to solve the problems. Okay then guys, all the best then, and I'll catch you in another section. Cheers!